So I'd like to welcome everyone to the early in the morning to the 33rd discrete mini conference. So every year we pick a theme, and so this year our theme is discrete math bio, and so half of our talks are going to be focusing on that theme, and the other half are going to be from a more broader discrete math setting. So a couple announcements is definitely no food in this room. Drinks, be careful. Okay. Yeah, don't spill the coffee. Please don't spill coffee. What else? This is our newish, the Watt Family Innovation Center. So this is, it's a very nice building for us. So for this room, there are whiteboards are all around the room. The wall is a whiteboard. There's some whiteboards here, whiteboards out there. There will be box lunches provided, so stick around for lunch. And if anyone parked and doesn't have a parking pass, let me know, because I will make sure you get a parking pass. For the other organizers, Wayne will be showing up sometime later today. He's busy this morning. And Svetlana is on sabbatical in Europe, so she's definitely not coming. All right, so I'd like to introduce our first speaker, who's Martha, who's going to be from the University of Kentucky, who's going to be talking about, so maybe you should introduce your title.
A minimaj-preserving crystal on ordered set partitions.
Is that loud enough, or do you want to turn on the room speakers? Do you want it on?
I can speak louder, definitely.
It's a small room. Okay. Yeah. All right. We'll take it away.
So thanks. I want to thank the organizers for the invitation to speak, and I also want to mention that this is the first time I've given a talk where the slides were in front of me instead of behind me. So we'll see how this goes. I'm really not used to seeing so many copies of my talk all at once. So, right, and I also want to make an apology for a typo in our program, because this word minimaj, I will explain what that is a little bit more in the talk. Google likes to autocorrect that to minimal. So it was autocorrected to minimal on the program. And so this is joint work with this lovely group of people. The work started at a workshop in Banff, and this was us working really late, and we decided to take a selfie. So this is joint work with Harris, Orellana, Schilling, Coleman Narejo, Bankart, Panova, and you. Okay. So the theme of this work is about symmetric functions. But here's a little bit of a background for this problem that we started working on. So it started with the shuffle conjecture. But so that was work done by Hagelin, Heyman, Laura Rimmel, and Gulyanov, and they came up with this conjecture around 2005. So they studied the space of diagonal harmonics. So these are polynomials in the variables x1 through xn, y1 through yn, and they vanish under some partial differentials. So a quick example here, a small example, is when n is 2, so these are polynomials in the variables x1, x2, y1, y2, right? This space of diagonal harmonics is spanned by these three polynomials, right? So a result that was obtained by Heyman in 2003 was that the dimension of these spaces is n plus 1 to the n minus 1. So you might recognize that number as the number of rooted trees on n, or the number of labeled trees on n vertices. Right, so it's a very nice combinatorial number, and there's actually a lot of nice combinatorics that underlies the space of diagonal harmonics. Right, so not only is it just some vector space, there's a group action. So here Sn is the group of permutations on n symbols, and it acts diagonally on this space of polynomials. Right, so it permutes the indices 1 through n amongst the x variables, and it permutes the indices 1 through n amongst the y variables. So for example, here's a permutation written in cycle notation, 1 through 2. So that just acts by sending the index 1 to 3, 2 to 1, and so on. So in this case, when that permutation acts on this element, and this is an element in DH3, right? It permutes the terms, but in the end, it just fixes. It actually fixes that polynomial, and it just sends it to itself in this case. Right. So we have a group action on a vector space. So it's an Sn module, and we can ask, how does this module decompose into simpler parts? How does it decompose into irreducible Sn modules? So in the theory of group representations, right, anytime you have a finite group acting on a vector space, it will break up into a direct sum of simpler components. Right? So each module is irreducible if it doesn't contain any submodules, any proper submodules. Right? So the theory for Sn modules is really nice. It involves partitions. Right? The whole set, the entire set of irreducible representations for this metric group Sn are indexed by partitions of n. Right? And those irreducible modules are called spect modules, and they're denoted here by S superscript lambda. So for example, when n is 4, there are 5 partitions of 4. So a partition is just a list of positive integers that are non-increasing, and the parts sum up to n. So for 4, there are 5 partitions, integer partitions listed in the top row in that example, right? And they can be represented by shapes. So here, right, for the first one, when the partition is just a single part of 4, that can be represented by four blocks stacked together in a row. Right? The partition 3-1 can be represented by 3 blocks in the top row, followed by 1 block in the next row, and so on. So when n is 4, you actually get Tetris pieces indexing your Sn modules. So that indexes our entire set of irreducible modules. And there's a very nice formula for us to compute the dimensions of these modules, for example. It's called the Hook-Lake formula. And I'm not gonna tell you exactly what that is, but right, these 5 modules have dimension 1, 3, 2, 3, 1. And there's, in particular, right, the module that's indexed by that horizontal strip, right, that Tetris piece that's just the horizontal strip, that's called the trivial representation. So it's a one-dimensional vector space, so that when your permutation group acts on any polynomial in that space, it just fixes every single polynomial. Right? At the other extreme, if you look at the Tetris piece that's just a vertical strip, right, that's another irreducible representation that's dimension 1, and that's known as the sign representation. So what happens there is, if you have any element in that one-dimensional vector space, and you have your permutation group act on it, when you have a transposition acting on it, it will just flip the sign of your polynomial. So instead of f, it will go to negative f. Right, so back to our example, diagonal harmonics, n equals 2. Right, that was a 3-dimensional S2 module. So the irreducible modules there are only two kinds, right? Either the one that's indexed by the horizontal strip, or the one that's indexed by the vertical strip. So either the trivial representation or the sign representation. So how does this break down? In this case, it breaks down according to the span of the basis vectors that I exhibited, right? The permutation group S2 fixes the polynomial 1. So that corresponds to a copy of the trivial representation. And then the other 2 basis vectors, x1 minus x2, y1 minus y2, right? When you have that transposition acting on it, right, x1 minus x2 gets flipped to x2 minus x1. So both of those other factors, other polynomials, correspond to the sign representation. Right, so we can decompose it into irreducibles. So related to modules is this idea of taking characters. So specifically in this case, right, if you consider all the Sn modules for all n, that forms a ring under addition and tensors of representations. Right, there is something called the Frobenius characteristic map, and that Frobenius characteristic map sends these modules to some functions. Well, they're actually not functions, but it's called the ring of symmetric functions. And specifically here in our application, these irreducible spec modules get sent to something that's called the Schur function. So these Schur functions are written by lowercase s indexed by these partitions. And there's a very nice combinatorial definition for Schur polynomials. And it's the following. So the Schur function S sub lambda is a sum over something here I've written as SSYT of shape lambda. So what is SSYT? That's a set of semi-standard Young tableau of shape lambda. So what that is you have your boxes, right, stacked together that represents your partition, and you're allowed to fill those boxes with numbers 1 through n. And you have to fill that shape so that along each row it's weakly increasing, and along each column it's strictly increasing. So here's an example of a Schur function of shape 2, 1. So I'm allowed to fill it with numbers 1 through 3. And I've been told that 5-year-olds, if you give them enough time, they can figure out how to compute Schur functions using this formula. So there are 8 possible fillings here, right? Weakly increasing along rows, strictly increasing along columns. And how you turn this into a Schur polynomial, you look at the filling of the shape, right? If you fill it with, say, 1, 1, and 2, that corresponds to the monomial x sub 1 squared times x2, and so on. Right, so you'll notice there are 8 terms. The last 2, they have the same kind of filling, 1, 2, 3. So that corresponds to 2 terms of the monomial x1, x2, x3 right at the end. Right, so we actually need something a little bit fancier than just the Frobenius characteristic. Right? The Frobenius characteristic before, it just sent those irreducible modules to Schur functions. I want to grade them, give them a grading. So in this example, back to diagonal harmonics 2, right? So according to the degrees of these basis polynomials, right? So for example, the constant 1, that just has degree 0 in x and degree 0 in y. So that has bigraded degree 0, 0. And then the next polynomial, x1 minus x2, that has degree 1 in x, degree 0 in y. So that bigraded degree is 1, 0, and similarly for y1, y2, that has bigraded degree 0, 1. So the bigraded Frobenius characteristic just is a little bit fancier. We add some q's and t's to the formula. So for each irreducible module, we record its Schur function together with that bigrading. So it's q to the I and t to the j. And so for this example, when we take that bigraded Frobenius characteristic, we get Schur function S2 plus q S11 plus t S11 corresponding to the 3 irreducible modules. Right. So how do we compute this characteristic? So in Heyman's paper, he showed that this bigraded Frobenius characteristic is nabla En. So he hid a lot of the complications in that single operator, the nabla operator. And I also won't write out the whole thing, but it's quite complicated looking. Here, En is just an elementary symmetric function, right? It's another favorite symmetric function in the space of symmetric functions. So the question remains, how do we actually compute it? Because it's almost impossible to directly work with this nabla operator. It is so complicated. So here's what the shuffle conjecture is about. There's a lot of combinatorics connected to this space of diagonal harmonics that's really nice. And so the conjecture was you can compute nabla En combinatorially as, so here m sub mu is the coefficient of a certain monomial. Right, to compute that coefficient of a certain monomial, it's a sum over some combinatorial objects, which I'll explain in a little bit more detail in a second. So it's a sum over some combinatorial objects, and you just compute 2 statistics on these objects. You compute what's called the diagonal inversion of these objects, and you compute the area of these objects. And that's supposed to be the formula for this characteristic, this Frobenius characteristic. So continuing our example, right, we had the Frobenius characteristic was Schur function S2, QS11, TS11. If I change that into monomials, right, actually write out the monomials for that, we get x1 squared and so on, that line. So let's say I wanted to compute the coefficient of x1, x2 in that expression. right? In this case, the coefficient would be 1 plus q plus t. So the shuffle conjecture says there should be 3 objects that we can look at. We compute some statistics, and we should get 1 plus q plus t. So these objects are related to dict paths. Actually, let me pull up some pictures here. Right, but so the shuffle conjecture says this formula is a sum over Pn, which is a set of labeled dict paths. So quick refresher, dict paths are lattice paths from the origin 0, 0 to the point n that don't fall below the line y equals x. Right, so you can take steps that go up, steps that go east, I guess, east, right, but you can't fall below the line y equals x. And so we also want to label these. We want to label all the up steps with a label that's related to the monomial that you care about, the mu in the monomial. In our example, x1, x2, mu is 1, 1, because there's 1 x of 1 and 1 x of 2. So, right, let's just look at the example right there. In this case, 2 dict paths from 0, 0 to 2, 2. Right? But in the dict path, you either go all the way up and then over, or you take little steps, but they're just 2 shapes. But then because we have these labels, in this case, you want to label it with 1, 1 and 1, 2. Right? There are actually 3 labelings. And there's one condition where when you label, each vertical run has to be increasing. So there's only 1 labeling for the path that goes all the way up and then across. So the area statistic on these diagrams is really easy to define. So the area is just the number of boxes, entire square boxes that fill underneath your dict path. So when your shape is that staircase, right, 2 little steps, it's 0 area because there are no boxes that can sit entirely underneath that staircase. But when the path just goes straight up and then across, right, I've shaded the area that's underneath that path. So here AI stands for the area of that row, right? So if you look at the very last diagram, a sub 1 is 0, but a sub 2, there's area 1. So area is easy to understand. Now diagonal inversion, a little bit less intuitive, but it has something to do with comparing the labels on rows that are either have the same area or where their areas are off by 1. So I won't go into too much detail about that, but you just look at the labels comparing rows with almost the same size. So you can compute the diagonal inversion for every row, you sum them up, and that's the diagonal inversion statistic. And then if you look at this collection of 3 paths, right, 3 labeled paths, you just record t to the area, q to the diagonal inversion, sum them all up, and you get 1 plus q plus t. So here's just a slightly bigger example, right, in case that one was really small. Right, just any lattice path, you can take north steps, you can take east steps. The labeling here is a little bit different, but again, area 2, you can compute diagonal inversions and so on. Right, but actually, let me go back for a second. Right, the shuffle conjecture is actually now the shuffle theorem. This was proved by Carlson and Mellett in 2015, and they used a lot of algebraic geometry to actually get at this very combinatorial result. But so that was proved in 2015, and some people that originally came up with the shuffle conjecture said, well, we can come up with an even harder conjecture. This is called the delta conjecture. So this was conjectured by Hagelin, Remmel, and Wilson in 2016. So we still have the elementary symmetric function En, and then now instead of the nabla operator, they have something called the delta operator. Again, it's some very, very complicated differential type of operator, but their conjecture is now this expression at the top of the slide. All right, so this is a generalization of the shuffle conjecture. when the delta operator, when we set k is equal to n, that is the special case that recovers the shuffle conjecture. So that's the origins of the story. The central object that my co-authors and I have been studying is this expression that's on the right-hand side, this val nk x qt. So val nk x qt, it's some polynomial in the variables x1 up to xn, and it's got some q and t coefficients as well. So let's see. Right, so one more thing I want to mention about this formula up here, the val nk, right? You'll see here there's a sum p in LDN. So LDN is similar to what we were talking about before, labeled dig paths. Here, LD does stand for labeled dig paths. So we're considering the same kinds of objects, dig paths with some labels. You're still looking at the statistics, diagonal inversion and area. But then there's this extra thing that we have to consider called the contractible values of a path. So in this example, there are two contractible values in the fourth row and the fifth row. So what happens is, if you take this diagram and you just rotate it about 45 degrees, the path looks like a mountain range. All right, so you have mountaintops and you have valleys. So a valley is contractible if so here's a valley, right? At the fourth row there's a valley. If you remove this horizontal step and you shift it over, so for example you get this diagram, and then the step that you remove, you stick it at the end. Right? If that remains a valid diagram, then you have a contractible valley. So we have contractible valleys in the fourth row and the fifth row, but for example, not the second row. Right? The second row, if you remove this step, shift the whole diagram over, that filling in the first column is no longer strictly increasing, so that's not allowed. So 2 is not a contractible valley, but 4 and 5 are. So you have to keep track of these contractible valleys, and that's a part of the expression, and that's why these polynomials are called val. Right, so we actually study in our work a specialization of this polynomial. Q's and T's are a little bit too much to deal with sometimes, so we specialize at set Q equal to 0. And a result of Hagelin, Rummel, and Wilson is that when you do that, there's a very simple expression for this val polynomial. It's a sum over ordered set partitions, and we have to keep track of a statistic called minimaj. So set partitions, let me bring up the example. Right. So let's think about ordered set partitions of 4 elements into 2 blocks, because that's this example. So for example, if I have a set 1, 1, 2, 3, and I want to partition that set into 2 blocks, I want to do it so that every block is a set. Every block has distinct integers. Right, so in the first case, if my set is 1, 1, 2, 3, I can do that in 4 ways. And so you consider all the different sets for which you can partition your multi-set into 2 blocks so that every block is a set, and we end up with 15 set partitions, right, denoted with we separate blocks of this partition with a vertical line. And so this proposition of Hagelin, Rummel, and Wilson says just look at your 15 ordered multi-set partitions, right, compute something called a minimaj statistic. That gives you the t coefficient, or the t exponent, and then you also just record the set partition gives you the x monomial. Right, so a set like 1, 1, 2, 3 will give rise to a monomial x1 squared, x2, x3. Right, so before I talk about what minimaj is, I want to review some of the classical permutation statistics for this metric group. So the major index of a permutation, here pi is written in one-line notation, right? The major index is the sum over descents of the partition, or of the permutation. And a descent is when pi I is greater than pi I plus 1. And then in the major index computation, you just record the position where that happens. So that's major index. Another statistic that was studied classically is called the number of inversions. And that's when you look at the one-line notation of a permutation and you look at pairs. Pairs where pi I is bigger than pi j. And so a very classical result, this is due to McMahon, and that's 1913, not 2013. Right? His result was that major index and inversions are equidistributed over the permutation group. So when you sum over the n factorial permutations and you record major index, that's going to be the same distribution as when you sum over the permutations and record the inversions. And in fact, something else nicer happens. When you sum over all those q's, right, that actually is the q analog of n factorial. But q analog happens when you replace n with 1 plus q squared up to q to the n minus 1. So in this example, we've listed the 6 permutations of S3. And you can compute the major index. For example, if you look at the permutation 132, right, a descent occurs between the number 3 and the number 2, so that's noted by a little dot after 3. So if you record the position where the descent happens, it occurs at the second integer, so major index for 132 is 2. And if you want to look at inversions, in this example, I've noted the pairs of inversions through a little green arc. You count up the number of arcs, and that's the number of inversions, and you'll see that there's an equidistribution between the two statistics. And so these are very classical quantities that we're studying. But now, what is minimaj? So this is defined on ordered set partitions. So if we have an ordered set partition pi, right, written in a very sane order, every single block is just increasing. Right, we can define a different way to write this, called the minimaj order. So what we want to do is start from the last block, that's still increasing, but then we work right to left. Right, we want to start ordering the next block, 3, 1, in a way, so we want to split the second to last block, 3, 1, so that we have a subset of integers that are less than or equal to 1, 1 being the smallest element in the block to its right, and then we want to look at the collection of numbers that are greater than 1. And so we separate the numbers that way, and we put them in this order. Numbers that are less than or equal to 1 goes at the end. Numbers that are greater than 1 goes in the beginning, and that's in increasing order. So you start doing this working from right to left, and you order the rest of your blocks that way. And that's minimaj order of the set partition. Now we can look at descents with this thing, still look at where there's a descent occurring, note it with a little purple dot, and minimaj is then basically the major index of the set partition written in that specific order. Right, in this example, the descents occur in positions 2, 7, 10, 11, adding all that up. This set partition has minimaj 30. And this is called minimaj because it's actually the minimum of the major index when you order that set partition in all possible ways. So that's why it's called minimaj. So what happens for our example val for 1, we can compute the minimaj for every single term of the 15 set partitions. That's t to the minimaj, and then remember we talked about Schur functions, symmetric functions. We can rewrite this in terms of the Schur function basis, and it becomes a lot more compact. Right, just 4 terms. T squared S211, T S22, T S211, S211. And in fact, it's a theorem that this Val polynomial is T Schur positive. So that means when you express it in terms of the Schur function basis, the coefficients of each Schur function is a polynomial in the T's with non-negative coefficients. So that's really nice, because if all your coefficients are positive, as a combinatorialist, you think there must be a combinatorial formula for this. And in fact, so this was proved individually by Rhodes and Wilson, and they both give a very concrete, specific formula for computing this in the Schur function basis. But so, what we were interested in was to show that this polynomial is T-Schur positive using a different mechanism called crystal bases. So a brief history of crystal bases. They were introduced by Kashiwara and Lustig in the 90s. And it basically is a combinatorial structure that mimics representations of quantum groups and Lie algebras. So a crystal can be defined for any root system. Here we only care about the type A system. And they're defined using, they can be defined using axioms, where you specify something called lowering and raising operators. And even better, a crystal, there are some pretty pictures associated with them. You can picture them with directed graphs. And edges represent these lowering operators of these crystals. How much time do I have? I didn't.
15.
So, back to our semi-standard Young tableau. Right? Classically, crystals were defined on semi-standard Young tableau. So remember, those were these fillings of these shapes with 1 through n, weakly increasing along rows, strictly increasing along columns. So here's the crystal, that directed graph that represents a crystal of the semi-standard Young tableau of shape 2-1. Right. How is this constructed? You start with what's called the highest weight tableau. So if I give you any partition shape, you just fill the top row with 1s, fill the second row with 2s, third row with 3s, and so on. That's the highest weight picture. And then we can start applying these lowering operators. In this case, there's always going to be n minus 1 of them, f1 through fn minus 1. And how are these defined? So if we want to define, say, f1, the f1 operator, you first take your tableau and you write it in reading, you come up with its reading word. So its reading word is obtained by looking at the bottom row. You read left to right, and then you move to the second bottommost row, read left to right, and so on. So you have its reading word, and then you look at the occurrences of, say, I and I plus 1, if you want to define f sub I. Right? If you see an I, you assign a closing parenthesis to it, and if you see an I plus 1, you assign an opening parenthesis to it. So some of them will match up, some of them won't. Right? If there is an unmatched closing parenthesis, then applying fi to this reading word changes that closing parenthesis to an opening parenthesis. So for example, right, at the bottom, on the left-hand side, let's say I want to apply the lowering operator f1 to the tuple 1, 1, 2. First turn that into the reading word, 2, 1, 1. You assign your parentheses, and the rightmost unpaired parenthesis, that gets flipped to an opening parenthesis, and that corresponds to changing that number from I to I plus 1. And then you undo that reading word, you fill up your shape again, and that gives you another semi-standard Young tableau. So that's the action. You start at the top of the crystal. That's the action of f1 sending you to a different crystal. And you can define f2 in a similar way. And then you just keep applying these lowering operators wherever you can. And at the bottom, right at the bottom, the filling 2, 3, 3, when you try to apply lowering operators, it no longer changes it to anything else. So that's where the crystal ends. And then this connected, this component, this graph, is a crystal. Now, remember we computed a Schur function at the beginning of shape 2-1, and there were 8 terms? Right? There are 8 terms in this crystal, and you sum them all up, right? Each tableau turns into a monomial. That is actually exactly that Schur function S21. So this is why crystals are a good tool for showing when a polynomial can be Schur positive. Because if you can define a crystal structure on what you're studying, then you can look at each connected component of your crystal, and that is a single Schur function. So you just count up your components, and you can show something is Schur positive if you can define a crystal on your objects. So we were interested in trying to apply crystal theory to show that our thing is sure positive. And the running example we've been doing, right, there were 4 terms, 4 sure functions, and each of them corresponds to one of these crystals. We were able to put a crystal structure on our object. So let's see. So this is our work. It's a little bit wordy, but basically we send our set partitions over to a tuple semi-standard Young tableau. Because for semi-standard Young tableau, there's an existing theory of crystals. So we send each set partition over to a tuple of semi-standard Young tableau, and we tensor the existing crystal structure to get one for our set partitions. So that basically is what all this is saying. All right, here's an example of what goes on. Start with an ordered multi-set partition, written in minimaj order. So we keep track of where the descents happen. The d's of i's here keep track of the distance between descents. The I sub 1, I sub 2, and so on, that keeps track of the number of blocks that occur between descents. And that data, it's all the details hidden in this formula and in this statement of theorem there. But basically, this data tells us the shape of certain semi-standard Young tableaus that we want to biject this to. Right, so we have a bunch of columns. You see we have a bunch of column shapes. And the last one is always this ribbon, some kind of a ribbon shape. So we color code some of these entries in our set partition. The first element of every block, we color red. And then in each block, if there's something behind a descent that's colored blue, everything else is colored green. That just helps me keep track of how I'm filling up the tableau on the other side. Right, so the red element fills up the tail part of my ribbon tableau. Right, this ribbon tableau here, the red elements fill up the tail end. I'm reading it from the bottom up. Right, fill up the tail end of that ribbon. And then basically, if you look at the green row and the blue row of numbers in my set partition, everything in front of the first descent, right, everything that's in front of this first descent, that's just the number 7, that fills up the remaining ribbon shape. Everything that's in front of the second descent, the 4 and 6, that fills up the 1, 4, and 6, the 1, 4, and 6, that fills up this column, and so on. Everything before a certain descent fills up the next column. And so, because these semi-standard Young tableau already have a crystal structure on them, we tensor that structure. That gives us lowering operators on those tableaux. Right. And we have this bijection. That construction that I just showed you was a bijection. So we just borrow those lowering operators and we can define them on our set partitions. So is that picture again? So basically, we can describe this Val polynomial now as a sum over these highest weight. Right? Every component of a crystal is generated by a highest weight set partition. You apply these lowering operators. So Val is a sum over these highest weight guys, and you just compute the minimaj. Right? So one of the hardest things about this thing was to make sure that all our operations preserve this minimaj statistic. Right? On every component, those set partitions have the same minimaj. Something that was a little bit surprising to us was that in this construction, if you look at, say, the very first component, right, the block sizes are different. That was something that was unexpected to us. Somehow the sizes of the blocks don't really matter. And I want to mention we were able to use our crystal structure on these ordered set partitions to prove something that the original authors of the Dalton conjecture were not able to accomplish. So Wilson, right, he studied a lot of these statistics, inversion, diagonal inversion, and major index. He showed that all of those were actually equidistributed over the ordered set partitions. And he gave beautiful bijective proofs. But separately, Rhodes showed that the statistics inversion, diagonal inversion, major index, and minimaj are actually equidistributed on the set of ordered partitions. But his proofs are entirely algebraic. So the one missing piece between these two stories is there a combinatorial, is there a bijective proof that minimaj is equidistributed with some of these other statistics? And we were able to use our crystal structure to accomplish that, to get a bijective proof that minimaj and major index are equidistributed. So actually, I think that's all the time I have. 5? Okay. Then I can keep going. Right, so I can describe a little bit about this last application that we got. So major index, I mentioned it briefly for permutations. How do we generalize that notion to ordered set partitions? So here, instead we'll put the ordered set partition pi into major index order. And that order is easy to describe. Every block is decreasing. Put it in that order. And then now we want to basically compute the major index for that. So remember, for permutations, you note where the descents happen. And you just sum up the positions where the descents happen. But now for this multi-set partition, we give it an auxiliary code V. In the first block, everything has code 0 except for the last element. Right? This is written in pink. Right? In the second block, every element gets this code 1 except for the last element, which gets 2, and so on. So the major index for ordered set partitions is still a sum over descents. We're still trying to note where the positions where the descents occur, but now we're summing up this auxiliary code. Right? So in this example, there are lots and lots of descents. Or you start summing up the positions where these descents occur, or you sum up the code where the descents occur, and that is the major index. This example has major index 27. So I bring this slide back up, or this example back up. We previously talked about how this ordered set partition is bijected to a tuple of semi-semi-jump tableau, a bunch of columns together with a ribbon. Right? If we look at those tableaux, that naturally corresponds to another ordered set partition in major index order. You just take every column and you just write it in decreasing order. Right? So here, there are actually 6 columns. That ribbon consists of 2 columns stacked side by side. Right? So there's 6 columns here, and basically what you might naively try to do, if you're trying to get a bijection between minimaj and major index, is to take those columns and just write them in major index order. But there is a very obvious defect in this idea, because we had an empty column. An empty column corresponds to an empty block, which was not allowed. So this naive idea didn't quite work. And also, if you compute the major index of pi prime, it's not, so before we had minimaj 30, major index for pi prime was 31. So almost, but not quite. But we can fix it. We can fix this by using a left shift operator. So, right, remember we had that empty block that shouldn't happen. So we can define this left shift operator L, and I won't go into all the details, but basically it's possible to define this so that we start shifting some of the elements into that empty block in a certain way. And in here, right, we shift the entire block 8, 6 into that empty block, and then the third block that contains 6, 4, 1, we just shift the 1, 6. There are rules that tell you how to do that. And then now, if you compute the major index of this left shifted guy, its major index is 30. So, in fact, right, but this naive way of looking at our bijection, coming up with these columns, and then doing this left shift gives us a crystal bijection, actually, a crystal isomorphism. There is before there was this crystal structure that had components with constant minimaj index. Now, basically, we have a crystal structure on these things where the components have constant major index. And moreover, this gives us a bijective way of showing that the statistics are equidistributed. And that's all I have for today.
Questions?
Back to the picture that I like. I like that picture.
So those crystal structures, they seem to me the digraphs, like they're very structured almost. They might even be series parallel. Do you know anything about this?
Series parallel.
So can an induced in shape happen?
No.
Is there anything that's
Well,
known
so
about
so
this?
for type this is a type A crystal. For type A crystals, an N shape cannot happen.
Okay.
I don't know. It can be more generalized, and for those cases, I don't know.
Questions? Let's thank our speaker. We have another talk in 5 minutes.